Okay, we can start the afternoon session. We'll have a single talk by Nikita Nekrasov, and he will tell us about content partitions from instantons.
Thank you very much. So I would like to talk about a few, several classes of models of statistical mechanics, you might call them, which originate from gauge theories and Sigma models in various dimensions, and which have interesting connections to all kinds of questions in mathematical physics: spin chains, random matrices, conformal field theories, therefore critical phenomena, and so on and so forth. But also they provide often a way to do the analytic continuation of models which I mentioned, where the parameters in which you can analytically continue could be integers, like the rank n of the matrix models, or could be reals, like the central charge of a CFT, or like spins, or number of dimensions. So all that could be complexified and using the models which I'm going to talk about. So at least from that point of view, they are interesting. But of course, for me, they were interesting because this is what many questions in gauge theories well, in fact, in the whole range of dimensions from 2 all the way to 9, reduce. So and the counting is as follows: that if you work in 2 and 3 dimensions, typically you get partition functions which are sums over integers, or some finite sets of integers. A typical example is the hypergeometric function, which, of course, is, I mean, it's a classic mathematical physics object. But so usually it's associated with the representation theory of SL2. Of the Lie algebra of SL2, but in this context, it arises as the count of worldsheet instantons also known as quasi-maps, where, so what you're mapping is S2, and where you're sending S2 is the so-called local P1. So it's a non-compact Calabi-Yau threefold, which is a total space of O-1 plus O-1 bundle over P1, which can be described in the language of gauge linear Sigma model or symplectic reduction, like as the, so this is the space. So this is what you get by taking 4 complex dimensional vector space and taking the symplectic quotient, or maybe to save time, just taking the quotient with respect to the action of the group C star, which acts with charges +1, +1, -1, -1 on the 4 coordinates of C4. And so this P1 is, roughly speaking, it's a quotient of the first 2 copies of C divided by the C star, which simultaneously scales the 2 coordinates, and then the other 2 will provide the fibers of this bundle. Now, a holomorphic map of S2 into such object, it's a collection of, so you need a 4 tuple of polynomials of degree d, d, minus d, minus d, and obviously these guys are 0 if d is non-negative. But the fact that, so the way this count is done is, so it's done using supersymmetric formalism. And so if you have some, so if the equations which you try to solve don't happen not to have solutions, then typically you have solutions to a dual set of equations. So there's certain dual space. And so, so these fibers do make a contribution. And to make the long story short, so if you write Gauss's representation of the hypergeometric function, so as the power series, so Q will be the parameter which counts the degrees of the map. And so I will have d factorial and the Pohammer symbols. So in this formula, so these 2 terms in denominator come from the contribution of the polynomials describing the maps to the first 2 lines. And the numerator is the contribution of the abstractions for the other coordinates. And that's, so I understand it's very kind of brief, but that's just to give you the idea of what kind of counts we are talking about. So this simple ratio of factorials, I mean Pohammer symbols or gamma functions, it's an integral of essentially it's equivariant integral of 1 over the modular space of quasi maps of degree d of P1 into that Calabi-Yau threefold. And then the parameters A, B, and C have a meaning of the equivariant parameters for the global symmetry of that space, which rotates these coordinates. So I have C4, so in principle I can have 4 independent rotations, but one of them is trivial because we're gauging by 1 C star. So we're left with 3 parameters, and these are essentially A, B, and C. Now, if you try to look at the geometry of that space, so it's a toric manifold, and you can project it onto a, so you can take a quotient of that space by the action of the compact torus. You will get a 3 real dimensional convex body, for which I just drew a projection onto a plane. And so it will, that's the boundary. So you have some edges, some vertices, and you should think of the rest of this body as coming out of the blackboard. So these are kind of planes. It's a non-compact polytope. And so the size of, so this finite edge, it's actually, this is the representation of P1, of this base of this vibration. It's a 2-sphere. The size of this 2-sphere is not visible in this description. You need more detailed description of the space. But roughly speaking, Q is e to the minus the area of P1 plus a certain phase, which is the, in string theory language, it's a period of a B field. Now, the hypergeometric function, as we know, it's not really a function. It's actually it's a function valued in a two-dimensional vector space. So this so in defining this space of maps, I should be more actually careful. I should specify certain boundary conditions, and so there is a boundary condition at one point in the source P1. Which should map to one of the invariant points, fixed points on X of the global symmetry action. And there are two such fixed points. So there is these two vertices. And so the two ways, the two solutions, two local solutions of the hypergeometric equation, they actually correspond to these two vertices. So the other one will be obtained by simple reshuffling of parameters A, B, and C, and multiplication by some powers. So that's a simple manipulation. But then what the hypergeometric function allows you to do, you can also analytically continue to other values of the parameter Q, right? So it has the hypergeometric equation, which this is a solution, has three regular singularities at 0, 1, and infinity. And so we can re-expand the solution around different points, in particular when Q goes to infinity, which geometrically would mean that the area of this P1 becomes negative and goes to minus infinity, which turns out to correspond to a certain transition in the geometry of the Calabi-Yau space, which is called the flop transition, where this original P1 shrinks to 0, but the other P1, which you get by taking the ratios of the coordinates 3 and 4, becomes of finite size. And so that transition is actually nicely described by the properties of hypergeometric function. There is the third point, Q equals to 1, which I have nothing, I don't know how to interpret in this language. Okay, so that was just a warm-up example. So this is what you get in dimensions 2 and 3. So this is the partition function of a two-dimensional, typical two-dimensional supersymmetric gauge theory. If you replace factorials and Pohammer symbols by the Q analogs, that's what you'll get by going up in dimensions. So if instead of S2, you study a three-dimensional analogous theory, now compactified on S2 cross S1, that will lead to the Q deformed hypergeometric functions and so on and so forth, different Q. So I usually denote the Q which counts instantons with some slash here. So that's the other Q. And the Q which is in Q deformations, it has to do with a certain geometric feature of this manifold where you take so you slightly squash this product by making the S2 rotate as you go around S1. And so this Q will have the so geometrically it's a phase describing the way you rotate the two-dimensional sphere in going around the circle. Now, if you go to higher dimensions, so if you go to 4 and 5 dimensions, then somehow the integers which we sum over in lower dimensions in 2 and 3 acquire a new structure. So now we'll get the sums, typically we'll get the sums over partitions of integers. And that's due to the following obvious phenomena. So what are these integers? So these integers which I was summing over, they were instanton charges. So instanton charges in the present context, these are some topological characteristics of the particular space of fields we are integrating over. So when you map something two-dimensional into something higher dimensional, well, the invariants which you have are associated with the degrees of the map, and so these are usually elements of some lattice, so which I call maybe in a slightly derogatory manner just collections of integers. Of course, the lattices could be more complicated, but in the first approximation, these are just collections of integers. But now, if my space-time is now four-dimensional, so it's now four-dimensional space-time. So I still have non-trivial instanton configurations, which, for example, if my theory is the gauge theory with some gauge fields A, the instanton configuration will be characterized by the Pentragian class of the associated gauge bundle. So it's you would say it's again just an integer, but when you do things while taking into account the symmetries of space-time, and so if my space-time is R4, which I can compactify, so the symmetries which I have are the rotations or the spin covers, and so I have two independent space-time rotations. And so in doing all various integrations over the, let's say, modular spaces of instantons, so this is what my gauge theory partition function will reduce to. So this is the modular space of gauge configurations which solve the equation that the curvature is anti-self-dual, modular gauge symmetries. And so this becomes a sum over U1 cross U1 invariant instantons. And this is where the partitions start appearing, because now, so in general, the solutions of this equation, they tend to kind of be characterized by localized distributions of the energy. So the energy is the density of the Young-Mills action. So there are regions in space-time where when this density is large, and otherwise it's rather small. So if you're interested in configurations which are invariant anti-rotations, then they all tend to be localized near the origin, but nevertheless, you can still have a different spread along two invariant planes. And so you can have a certain number of instantons which are spread in this way, and slightly smaller number of instantons which extend in orthogonal direction, and so on and so forth. So this is very roughly why the instanton charge will be decomposed as a sum of subcharges, which are kind of describing the way the instantons, before they stuck together and formed a point-like configuration, they stuck together along a certain plane in groups of D1, D2, DL, and then they collapsed along the other plane. So So having this extra freedom of moving in additional directions sort of responsible for now the elementary object being not an integer, which is the instanton charge, but a partition of integer into well, partition of integers. Okay, so and from that you can guess that again, if you go higher in dimensions, let's say 6 or 7, you'll get plane partitions, because now you have three orthogonal planes. So these are, we can depict as three-dimensional Young diagrams. So here we'll have Young diagrams. And if you go to 8 or 9 dimensions, you'll get solid partitions, which I cannot draw. So these are 4-dimensional Young diagrams. Now, the choices of models which you can start with kind of get narrow and narrow as you go higher in dimensions. So in 2-3 dimensions, you have an enormous amount of so you have all Calabi-Yau three-folds, not necessarily three-folds. I mean, you have the whole symplectic and complex geometry at your disposal. In 4-5 dimensions, you have fewer choices. In 6-7, even fewer, and in 8-9, it's essentially the model is essentially unique. But there is some way of going down in dimensions by various limits and degenerations, and so it suggests that maybe the plethora of geometries which you can have at lower dimensions is really the result of multitude of ways of degenerating and taking limits in high dimensions. So this is a kind of a dream of M theory, string theory, that there is one theory which lives high in dimensions, and then by various compactifications you can produce many models in lower dimensions. Okay, so let me now stay in dimensions 4 and 5, and let me just give you an example of model which is which admits an interesting set of observables, and from which we can get exact statements of some value. So it's a specific example, and it's called, so in certain classification, it corresponds to the A1. So it's A1 type example, which you should keep in mind that there is an AD classification, loosely speaking. So A1 means that you have only one. Well, it's the Dinkin diagram of one is just one vertex, no edges, and that in more physics language, this is the gauge theory with the gauge group UN, and it has 2n matter hypermultiplets in fundamental representation. It does, I mean, you don't need to know what this is for me to introduce the model. So the model is, so the random variables are n tuples, this n, of Young diagrams. the sizes, so of arbitrary sizes. So this is a grand canonical ensemble. And so this set on which I'm going to define some kind of probability distribution is just the nth power of the set of partitions. So this is now. This is not, of course, it's in applications to physics, to gauge theory physics. I'm not really talking about a probabilistic measure because my parameters, so I have complex parameters. So there are n parameters which are called Coulomb moduli and 2n parameters which are called masses. They are all complex, and there are 3 more parameters. So we need to. So these are equivariant, or we call them omega deformation parameters. And finally, there is one parameter q. So it's a complex number, let's say less than 1 in absolute value. So I'm now defining a measure. So the complexified probability, or we may call it amplitude. It's really more like a complex analytic continuation of a probability of having an n-tuple of partitions. And so it is, first of all, it suppresses the sizes of these partitions. So there is something like so here, if you work with partitions, you know this is the kind of a product of the content polynomials, where the content of a box. So this is my partition lambda alpha. And each box in this partition has the coordinates I and j, so that this box has coordinates 1, 1. And the content is here. So the content of the associated box is epsilon 1 times I minus 1 plus epsilon 2 times j minus 1. The usual content which people learn in the studies of symmetric group is the one when epsilon 1 is negative epsilon 2. So then it's the content really tells you the distance from the main diagonal. But this is a general content which gives certain weights to the horizontal and vertical directions, and these are precisely these 2 omega deformation parameters. And I'm hinting that has to do with the rotational symmetries of 4-dimensional spacetime. So that's in the numerator, and then there is a denominator where you take the product of pairs of things. So it's a box in lambda alpha, box it's product of the pairs of boxes, and this alpha minus beta, and there's somewhat more complicated expression which I actually don't even remember correctly. So it's arm of the box in the diagram lambda alpha defined relative to the diagram lambda beta plus 1 minus epsilon2 leg plus well, essentially epsilon1 plus epsilon2 minus the same thing. So the arm is a number of boxes which are to the right of a given box, and you can define it even if so for two diagrams. So so this is lambda alpha. You draw lambda beta, and so you need to compare the position of the box in the first diagram relative to the row of the second diagram. So that will be so this is the arm of the box relative to lambda beta. And the leg is similarly that number. So these are some integers which know about the geometries of these Young diagrams, relative geometries. And so there is some, you can say that there is some interaction between the different diagrams. It's non-trivial even when there is just one diagram. Okay. And so the main result is that certain four-dimensional gauge theory partition function reduces to the summation over all lambdas of this expression. So one's interested in the studies of the partition function, which so the partition function which depends on all a's, all m's, epsilons, and q has certain prefactors which I will not explain today. So there is alpha, beta, 1n. This is Barnes gamma, double gamma function, which depends on differences of the Coulomb moduli and has epsilons as its periods. So gamma 2 of x, epsilon 1, epsilon 2 is a regularized product of things like that. When ij greater than equal to 1. So there is a Z there is a way to define this product using Z regularization. I will not go into that. It's so it's gamma 2 in the sense that here you have zeros, or if you regularize differently, poles which sit in a quadrant, positive quadrant. Usual gamma function has poles which are on the half line, which is like a quadrant in the one-dimensional space. So this is the second iteration. And in all these models, so this is, remember, in the hypergeometric function, it had some gamma prefactors. So gamma functions, these are ordinary gamma functions. Here you have double gamma functions. Here you have triple gamma functions, and there you have quadruple gamma functions. But that's and then there is things like that. Gamma 2. Times the sum over collections of lambdas, mu lambda. Okay, so you might say that why would I mean, what kind of nonsense is this thing? Well, it turns out that you can say quite a few interesting things about this partition function and certain expectation values in this model. Okay, how am I doing with time? Okay. Okay, so let me say two facts about it. So there is an asymptotics when epsilon 1 and epsilon 2 go to 0 simultaneously. And in this limit, you can prove that this partition function has a geometric asymptotics where, so this is the leading term, then there are some leading directions. So this function f is governed by a family of curves. So this is related to an algebraic integrable system, which is, you can view it in two ways, as XXX spin chain with n. So n, that's the number of sites. And so the masses, so the two n masses determining, giving n spins and n inhomogeneities. And Q being the twist parameter. So it's XXX spin chain based on the Lie algebra of SL2, so A1. So that's the same A1 I started with. That's one way to look at this. Another way is to view it as the 4-point Godin model with the Lie algebra SLN. So practically it means that we have a 4-punctured sphere with punctures at 0, Q, 1, and infinity. And what I said classically means that you consider a family of meromorphic Higgs fields. So these are meromorphic one forms valued in the Lie algebra of SLN with first order poles at these points. So phi 0 z plus phi q at z minus q plus phi 1 z minus 1 with the following restrictions. So eigenvalues of phi 0 are essentially given by M1, M2, Mn minus 1 over n. Eigenvalues of phi q are given by 1 over n times the matrix 1 over n, 1 over n, 1 over n minus n minus 1, 1 over n. Maybe without that. Phi 1 similarly now uses the other n masses. And phi infinity, which is negative of phi 0 plus phi q plus phi 1, has eigenvalues m n plus 1, m to n, minus 1 over n. So you have 4 matrices two of generic type and two of this essentially scalar matrix plus a rank 1 matrix. The eigenvalues are fixed, but the rest is not fixed. So you consider all such matrices. The constraint is that the sum of 4 matrices is equal to 0. So it's a constraint. And up to the overall conjugation. So you collect. So the claim is that the space of such matrices is a symplectic manifold. It's a complex symplectic manifold of dimension 2n-1. It's easy to see what it is in case n equals to 2. So if n equals to 2, every traceless 2x2 matrix can be written in the form z x plus iy x minus iy minus z. Knowing the eigenvalues of the matrix phi means that you know x squared plus y squared plus z squared. So having 4 matrices whose eigenvalues are known is like having 4 vectors in a 3-dimensional space whose lengths you fix, but the condition that they sum to 0 means that you can form a closed polygon. So these lengths are fixed, and this transformation is equivalent to the rotation in 3-dimensional space. You have to complexify the picture, but that's only subtlety. So the space of such polygons is actually 2-dimensional, because once you know the length of the diagonal and you know the angle between 2 triangles, that completely fixes that picture. So that's 2-dimensional in this case, and for higher n there is some analog of that geometric setup. But okay, what's interesting is that it's not only complex symplectic manifold, it is also an algebraic integrable system. Namely, there is a fibration of the space over the n-dimensional, n-1 dimensional vector space, whose fibers are abelian varieties. So this abelian variety is actually the Jacobian of the spectral curve. The curve being the vanishing locus of the characteristic polynomial of this family of matrices. And so the coefficients of this polynomial, given all these constraints on eigenvalues, there are n-1 independent parameters. And so once you fix these coefficients, in order to reconstruct phi, all you need to know is a certain line bundle over this curve. That's the eigenbundle of phi, essentially. So phi can be, so for every solution of this equation, you have an eigenvalue of phi. So there is a corresponding eigenvector. That eigenvector somehow sweeps a line bundle over the curve. And that's line bundle is a point on this Jacobian. So, so this is the family of curves. So U are parameters, which you read off this equation. And the claim is that A and derivatives of f respect to A are the periods of the differential lambda dz over A and B cycles of that curve. So that's how the classical geometry of the family of curves arises from as a limit shape, in fact, of this partition function, which is a sum of the partitions. And the tool which is used to prove this is the certain set of observables which have very useful properties. And so let me just present it and I will conclude. So observable So the first observable, which is kind of auxiliary construct, it's a function of a parameter x and its value on the collection of partitions is a product. So it's a product over alpha. So it's a rational function of x of degree n, whose positions of poles and zeros depend on the geometry of Young diagrams. So given a Young diagram, there is a certain number of boxes which you can add to it so that it continues to be Young diagram. And there is exactly one less number of boxes which you can remove from it. So these corners. And so the y observable as a function of x has zeros at the contents or shifted contents of the boxes which can be added to corresponding Young diagrams, and it has poles at the positions of the boxes which can be removed. So if I sample my, so if I take a random collection of lambdas and I evaluate this observable collection of lambdas, I know by looking at the zeros and poles of y where I can grow or where I can decay. So it's kind of it's a first hint at the growth process, that Young diagrams are not isolated objects. There is a way to move from one Young diagram to several others while growing or shrinking. Okay, so this is the guy which has poles and zeros, and it has an interesting relation to the measure I defined, and that relation can be summarized succinctly in the statement that the expectation value of y of x plus epsilon 1 plus epsilon 2 plus q times a fixed polynomial of degree 2n. So p, it's a polynomial whose roots are the masses. And the statement that it has no poles in x, and by examining its asymptotics at when x is large, you conclude that it's a polynomial. So it's in fact, it's a polynomial of degree n. And so from that, you get a lot of identities, because you can expand the left-hand side in x at large x, and so the coefficients of x to the negative powers of this object will have vanishing expectation value. So from that, already from that fact, you can derive various identities, which, while in McDonald's book on symmetric functions, some of these identities are non-trivial. So you can compute, for example, the sum over the single partition due to the lambda, the product of content polynomials of two content polynomials, and here is the Jack measure of lambda, which depends on two parameters epsilon 1, epsilon 2. So this is the arm leg usual denominator. Well, you can try to compute it using Jack symmetric functions, various identities, but from this relation, it's almost one-line computation. So it will give you that this is 1 minus q to the power m1, m2 over epsilon 1, epsilon 2, maybe plus. And well, it's a cute application of these identities. Now, I got this classical integrable system by taking the limit when epsilon 1, epsilon 2 goes to 0. So you can ask what happens if I don't take this limit. So for finite epsilon 1, epsilon 2, we actually get, first of all, we get quantum deformation. Of Godin and spin chain, and but we have two parameters, and so in addition to quantum deformation, we also get a non-stationary deformation. And I know what this non-stationary deformation is in the language of Godin. That's the equation. So there's an object psi which you can associate to this partition function. And so there's another observable, which I will not define for lack of time, which will solve the equation where H0 and H1 are operators. Which are obtained by quantization Godin Hamiltonians. So the spectral curve equation which I wrote gives you a bunch of classical functions on the symplectic manifold. In fact, n-1 function which Poisson commute. And so the quantization with epsilon 1 playing the role of the Planck constant will give you operators, and remarkably those will be commuting operators. And so when you have commuting operators, you can first pose the question of finding a common eigenvector, but you can also, well, it's known for Godin operators, and so this comes as no surprise that they can actually be included in the family of flat connections with the spectral parameter. So this additional parameter being epsilon 2. Now, what was known before, of course, long time ago, that you can construct these operators from the representation theory of current algebra, but it was not clear what was the meaning of this function psi which was solving it, because in the conventional conformal field theory, what you see here, this parameter epsilon 2 over epsilon 1 is so it's a shifted level of the current algebra, and so for unitary CFTs, this has to be an integer, certain bounds. Now, the spins of the representations in which one takes the Godin Hamiltonians are typically correspond to finite dimensional representations of the group, whereas here you have something of a different nature, and so these are typically infinite dimensional representations, which you can associate with this classical, or the orbits of this classical residues of the Higgs field. And so this is specific Godin model in the tensor product of representations of SLN, which are infinite dimensional. So this is a Fermat module of lowest weight, and then there are certain indefinite modules, which I will not describe, and Fermat module of the highest weight. So that the space of invariance in this tensor product is essentially, it's a functional space. It's a space of functions of n minus 1 variables. And that's the, so this is this observable psi, which you get as a sum over partitions. So this is also the sum over lambda 1, lambda n, but with the insertion of certain observable. So this is just the beginning of a kind of a set of relations where the correlation functions and the expectation values in these models of random partitions, they happen to obey the equations of two-dimensional conformal field theory. So this is the Knizhik-Zabolochkov equation. You also can get a BPZ equation, and you have, well, for different choices of spins, representations, central charges, so on and so forth. But typically, this is extended outside the usual realm of CFT. So the spins are complex, the representations are infinite dimensional, central charges are complex, which allows you to explore all various dualities which are normally not allowed for the conventional CFT. For example, the obvious symmetry of the four-dimensional theory where you can exchange epsilon 1 and epsilon 2 becomes this Lang-Lenz type duality, which inverts k plus n, which you cannot explore in the WZW theory, for example. So, so that's very useful. And also the fact that, so this was for four-dimensional theory, but in my presentation, even odd dimensions come in pairs. So if you go from 4 to 5, at the level of this partition sum, it's not a big deal. It's just you get the Q-deformed version of the of everything. So the parameters epsilon 1, epsilon 2 become Q1, Q2, and this is related to Q and T inverse in notations of old people doing shuffle algebras and young people doing shuffle algebras and McDonald theory and so on. So this is just a curious choice of notation, which I don't have time to get into. But you see, it's obvious that you should be using this notation because here you have a symmetry exchanging Q1 and Q2. And here it's kind of crazy. Why do you would exchange Q and T inverse? So then this would become a multiplicative relation like Z, Q1, Q2. So this is why you need a different Q notation. Anyway, so this goes on and on. This is much less explored in going in higher dimensions. You can go to now plane partitions and even solid partitions, and there are some preliminary results about the partition functions there, but less is known about the observables. So this observable is called the QQ character. QQ is because of the Q1 and Q2, so it has two deformations. It's not because somebody is crazy. But if one of the parameters goes to 1, then it reduces to a Q character introduced by, algebraically introduced by Frankel and Rezhetikhin long time ago. And then Nakajima at some point introduced QT character, which was fortunate because it was not the optimal definition, which differs from the QQ character. So it's this one is better because it has this nice analyticity property, which QT characters don't always have. Okay, so I hope I convince you that it's a rich area of research. It has connections to gauge theories where it came from, but also representation theory of infinite dimensional algebras. So here I focused on Godin, and where you see Katsmoudi and Virasoro and such. If you go in the spin chain direction, you will see Yangian, and then here it will become a quantum loop algebra. But since you can go up in dimensions, you get generalizations of those. So plane partitions, in some sense, can be viewed as a limit when n goes to infinity of that theory. So a single plane partition is just a sequence of ordinary partitions, which can go up to infinity, all the way to infinity. So that's the large n limit of that, and so that will give rise to this toroidal algebras. But there's also one more step where you can go to solid partitions with four-dimensional objects, and we don't know what's the algebraic structure there. So that remains a challenge. Thank you very much.
Thank you for the talk. Any question?
Yes. Yes, so this, in fact, it seems that once you do this double deformation, so it's no longer, as in the Godin case, it's no longer the eigenvalue problem you're solving, it's something else. You're looking for a family of states which evolve with parameters of the system in a certain way. And so for the spin chain, it seems like you will be not doing, so you're not considering a trace of the transfer matrix, you're actually considering certain matrix elements. And so this becomes a kind of a difference equation involving the matrix elements of transfer of the monodromy matrix, not the transfer matrix, but monodromy matrix. And so that indeed goes, by itself, it goes into a kind of open boundary direction. But this was the case of A1, and there is a direction of generalization here which I didn't get to, where you consider models which are associated to Dynkin diagrams. So then on each node of the Dynkin diagram, you'll have a different collection of partitions, and they will interact with each other in various ways. So then you may get spin chains associated to well, ADE groups or Lie algebras, and with some work in the Q-deform case, you can also go to the non-simple laced algebras. But I should say that the precise understanding of what's the spin chain interpretation of these equations is not yet accomplished. So together with my former students, Norton Lee and Sambyok Jung, we've been working on this for, let's say, 3 years already. So it's a bit complicated. It's more complicated than this. This is the result of my work with Sasha Cymbaluk. So to map the equations you get from these relations to this form, that's more straightforward. And with these fellows, we generalize this to a higher point KZ equation, where so this psi is the conformal block of 4 vertex operators. And with this young gentleman, we introduced some other so these are degenerate fields. The degenerate fields from the point of view of representations of current algebra. The interesting question is what does it mean to insert such a field at the level of this model? So that's it's a separate story. Maybe, okay, well,
I just wanted to ask, what's the gauge theory definition of Y? Is it like adding instanton and anti-instanton pair? What's the gauge theory definition of Y?
Oh, Y. Oh. No, Y is so Y is the properly regularized. Y is a local observable. It's an observable in gauge theory. So Y of X is essentially the determinant. It's essentially the characteristic polynomial of the scalar in the vector multiplet. But this is naive because this should be a polynomial and this is not a polynomial. So it's more like this combination corresponds to this polynomial. So Y is the generating function of the single trace operators. One over L x to the power L minus trace phi to the L. So you see, if phi were a classical matrix, this series you could have resummed and obtained just the determinant. But when you take the products of these operators in the presence of instantons, there are like instanton corrections. It's a quantum multiplication. And because of those corrections, in itself, it's no longer a polynomial in X. But there is one instanton correction in this case, which makes it into a polynomial. If the theory which I defined, I started with, is engineered as a theory on a stack of branes. So take a collection of D3 branes in type 2B string theory, then such an observable can be engineered by introducing a brane which lives in the transfer space, which approaches this stack of branes at one point. And then this parameter X would be distance. So these guys span 4 dimensions. This guy spans another 4 dimensions. You have 2 transverse dimensions. And so this is a point in this space, and this is another point here. And so this is X. So X has meaning of distance in that space. Yes.
So I'm curious about that. I think that's on the top left board because that's exactly the Z measures of partition. There's the parameters for that.
Yes. It's well, they introduced as an example of the measure you can define using symmetric functions, if I remember correctly. So my methods give ways to prove some identities about the measures. Yes, so some of the things. Well, so it depends on. I mean, for example, if I give you the general n case of that measure. So it depends on additional parameters, and it's no longer an elementary function. It's a new special function. It can be identified as a conformal block of a W algebra, but a priori it does not simplify. However, if you fine-tune your parameters, for example, if some of the masses differ from some of the Coulomb parameters by an integer multiple of epsilon1 plus another integer multiple of epsilon2, then it simplifies, and that corresponds to having a degenerate field in the language of CFT. And so that's at least in some cases where Borodin asked me to simplify his calculations, that's the way it works.
Another question?
Maybe I should, okay, I just want to say, I wanted to say something which was connected to Alex's talk, but I never get to say this, but let me just say this, because of course these partition sums, they have a long history, and back in the 90s, so more 25 years ago, I was studying them as residues, as multiple residues. So Z can be also written as a sum of multiple residues. So it's a k-fold integral. And the measure here will have the form. I mean, I hate this notation, but let me just use it for the sake of the argument. So I not equal to J. I mean, I hope Weierstrass doesn't see this from his brief. Times something which is one particle. I will not explain what this is. So this zeta is the function which in this. So in the so in the models, in the two-dimensional models, zeta would be something like 1 minus z, 1 minus qz. In the four-dimensional, five-dimensional models, this would be and if you go in higher dimensions, it will grow. So this ultimate model with which corresponds to 8 and 9 dimensions has this function which has 4 terms in denominator. And 4 terms in the numerator. Where the product of 4 q's is equal to 1. And because of the nature of these integrals, so if you try to express them in terms of symmetric functions, that will give you naturally this Heisenberg algebra which you were talking about. It's nice that now there is some algebraic theory. So 25 years ago, when I was looking at this, I was trying to use some CFT to simplify these integrals, but it always seemed to be too singular to me. But well, apparently that's because I was getting numbers, but instead you should be getting elements of some non-commutative algebra. And so that's as Alain Kohn used to say that if you have some singularity in the commutative world, try to make it non-commutative. So then. Okay, thank you.
More question? Okay, let's thank the speaker again.